Hello and welcome to another video. In this video we're going to be working on maximum width ramp. And in this one you have a ramp which is an integer array and you have a pair. And so in order to make this ramp, basically the ramp has to look like this, where the value at j has to be greater than or equal to the value at I. So, and then that value is j minus I. And then given an integer array nums, return the maximum width of a ramp in nums. If there's no ramp, return 0. So in this case, it's going to be, this is 0, or this is 1, and then 2, 3, 4, 5. So it's these two locations right here. Actually, let me use this one. Yeah, here we go. So it's these two locations right here because this value is bigger and this index difference is 4. So that's what it would be. And then in this case, it's these two because the values can be the same, and this index difference is 7. So basically, ideally, for every index, we want to figure out like what's the farthest index from it to the left that is smaller than or equal to it. And if we can do that efficiently, then that's how you solve these problems. For example, for this, we can say like, okay, is there an index to the left that's less than or equal to 0? And what's the farthest one that there is? In this case, it'd be like this and so on. So that's kind of what we have to do here. And you can obviously like brute force. So the brute force would be like, okay, you're given an index. Let me just go left and find every single index that's smaller, and let me keep track of like the leftmost one that's smaller. In worst case, it's going to be unsquared. So we need to do better than that. And there's kind of like two solutions that I think are pretty straightforward. Maybe there's a couple more, but yeah. And one has to do with sorting. So basically, our index to the right has to be, like, our j has to be bigger than I, right? And then our left number has to be smaller. So one thing we could do is we can actually sort all of these indices, and we could sort by the number. So let's take a look at what I mean by that. So let's say we look at this first example. Actually, let's use this. Okay. And so let's say these are numbers, and you can just write like a custom sorting function in whatever language to do this. So 608 to 15. So basically we can say like, okay, well, let's just take this. I think I can also, yeah, make this bigger. Okay, so anyway, so we can just sort these by the number. So we'll sort all the indices by the number. So the sorted version will be like 0 will be first, and then, whoops, yeah, and then 1, and then 2, and then 5, 6, 8, right? So put the 8 over here, put the 5 over here. So we're basically going to maintain the indices in an array, and we're going to sort by the original number. You could store like tuples or whatever, and that would kind of do the same thing. So you're going to have something like this. And now what we can do is, because these indexes are sorted by the number, we know for sure that every index, everything to the left of that, has a smaller value. So like, if this is a j, all of these can be an I, provided, as long as you know obviously j is bigger than I. So what we can do is we can just store the smallest index seen so far as we traverse, and then get an answer that way. So for example, like here, the smallest index we've seen so far would be 1, and then for 4, 1, 4 is a ramp, and then for this, 1, 3, 1, 5, and then here, the smallest index is 1, so there's nothing, and then here it's 2, 1. And that would work, right? Because 1 is the 0 value, so all of these pairs would be the best ramps for that number, right? Like for this 8, this is the best. Or actually for this 8, this would be the best. So this 8 actually, yeah, this 8 would be this thing right here. So that's kind of the idea. You just store your indexes, and then you just keep track of like the smallest one you've seen so far, and then for every index you just subtract the smallest ones you've seen so far, and that'll give you your best ramp. But you need to do a sort here, so that's going to be n log n, so there's something better. And the better way to do this is realizing this kind of, I think there's maybe a few ways, but basically we need to store like what are the things we care about and what are the things we don't, right? So for every number, we need to figure out like what's the smallest number, not the smallest number we've seen so far, but what is the number that's farthest away from it that's smaller or equal to it. So let's say our numbers are like this, and let's say we care about these some things over here, right? We're going to try to figure out some things over here for these numbers. For these numbers, let's call it ABC. We're going to try to find a ramp where j is one of these. And as we're trying to find these, let's say the numbers on the left are like 0, and then 6, and then like 8. Well, this 8 is never going to be used at the left side of a ramp for anything on the right because we just need j to be bigger than I. So if j is bigger than or equal to 6, it's obviously, or sorry, if j is bigger than or equal to 8, it's going to be bigger than or equal to 6, right? So for every number that j is bigger than, if j is bigger than this, it's also going to be bigger than this, and also 8's closer. So basically when we get a number that's bigger than a number we've seen before, like that's never going to be a good number to pick, because if we have a smaller number on the left, that's always going to be more likely to give us the ramp, and it's going to be a wider ramp. So anytime we encounter bigger numbers, or even the same number, that's going to be useless. Like if we have a 0 here and a 0 here, well, any number that's bigger than 0 will also be bigger than this 0, so we'd want to use this as the left side of the ramp, because that would give us a bigger ramp, right, to all of these. So that's kind of the idea, is we want to store numbers in strictly decreasing order. Because in increasing order, like if we hit a number that's bigger than something we've seen before, that's never going to be a good number to pick as the left side of a ramp. So what we can do is we can take this and we can store numbers in strictly decreasing order. So we can just go left to right and store all this in strictly decreasing order. So that would be, like we hit a 6 and we're like, okay, well we don't have anything yet, so let's store 6. And this is called a monotonic decreasing stack. So then we hit an 8, or we hit a 0, and we check, like, well, is 0 smaller than the end of our stack? Yes. And then is 8 smaller? No. Is 2 smaller? No, no, no. So this is our stack. This is our decreasing stack for example 1. And then we can go through these numbers, and we know for sure that, let's draw these numbers again. So we can go through these numbers from right to left now. And let's see these indices. Get rid of this. So same numbers, 6, 0, 8, 215. And we can just check, like, okay, well, we have, so in this stack, we're actually going to store the indices. So in this stack, we're going to store this. You could store index, you could store tuple, but whatever. But you need to store where the index of these numbers are. And then we can basically traverse this backwards, and we can say, like, okay, this is index 5. This is index 1. So that means that this is the smallest number that is to the left of this, right? The smallest number to the left of this is this number. So this is a possible ramp. And so to calculate that ramp, we can just say, like, well, this is 5, this is 1, so that ramp is 4. And then the other assumption we can make is we can say, like, okay, if this is the left side of the ramp and we're going right to left, if we're using this as the left side of the ramp, the best right is going to be the one that's going to be farthest to the right. So if we're going right to left and we found a ramp here, there will never be a better ramp to the left of this number that will use the same number, right? Because all these are shorter. If these are possible, they're all shorter. So we can say, like, if this is indeed a ramp, this number will never be used again because it will never make a better ramp. And then we can check again. Is 5 bigger than 6? No, it's not. Okay. Actually, so yeah. Is 5 bigger than 6, right? So remember, we're comparing the value to the value, and we're storing the index here. So we'll just say like, is the value at this index bigger than the number at this index? And it's not. So now this can't be a ramp. So then we go left and we say, can this be a ramp? No. Can this be? And remember, because our stack is decreasing, if this number is smaller than the smallest number in our stack, which is the end of our stack, if we did have more numbers here, these would all be bigger. So if this number that we're currently on is smaller than the smallest number in our stack, we don't need to check the rest. So is this smaller? No. And now this works as a ramp. So this is a ramp of length 2. And remember, now that we used this ramp, no other ramp will be better using this number in it, right? Like this won't be better, this won't be better, because this is the rightmost number that we can use. And so we can basically pop off the stack. And then once the stack is empty, we're done. So our answer is 4. Let's kind of do the same thing with example 2. So let's build the stack. So again, our stack will be strictly decreasing. So we'll put on the 9, then we'll check, is the 8 smaller? Yes. Is the 1 smaller? Yes. Is the 0 smaller? Yes. And we don't want anything else because, like I said, if we hit a 0 again, this 0 will never be used as the left of a ramp. Because why wouldn't we just use this one? It's farther away, so it'll make a bigger ramp. So this is our stack, and now let's go through our numbers. And yeah, when you're looking for these things, like if something is strictly greater or strictly smaller, then look for these like monotonic decreasing or increasing stacks, because generally those end up working. It's kind of tricky to figure out how to make it work though. Like in the solution, it's not super obvious, but yeah, those are some things to look for, and they're pretty rare problems, so I wanted to do this one. And yeah, I'm not gonna do like every problem from now on. I'm just gonna do like kind of interesting ones because I have a little bit less time these days. So here, let's look at this. So here, this number is bigger than this number, so we can use this as a ramp. So 3 to 9, so that's length 6, right? And that would work. That would be this index to this index. So this is length 6, so we're gonna write that down. And we know that this is never gonna make a better ramp anymore because this is the rightmost index that can use this number. So we're only going left, so every other one would be worse, so we can pop. Now we could say, can we make a ramp here? Yes, we can. So this is length 7. So 7. And then this is never going to be used anymore again because we're only going left. Can we make a ramp here? No, we can't. So then we go left. Can we make a ramp? No, 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 no. And then we can make one here. This is length 4. 7's better. So now we pop this off. And we can make a ramp here. Length 5. 7's better. Now we don't have a stack. Yeah. And that's basically it. So we just make a stack of decreasing elements, and then we go right to left, and we say, like, let's just keep using elements while we can, and recognize that if we already use an element, we're never going to want to use it again with anything to the left, because that's going to make us a smaller ramp. Let's take a look at the code. Pretty straightforward. So we can say, yeah, we can basically say, let's make a stack. Let's go through the numbers. If the stack is empty, or if our current number is strictly bigger, right? Actually, sorry, strictly smaller, right? Yeah, because if the numbers are the same, well, we're just going to use leftmost. So we want strictly decreasing. So if our current number is strictly smaller, then we'll add it to the stack. And then we go backwards and we say, okay, well, while the stack's not empty, and while our current number is bigger or equal to the end of the stack, then we can make a ramp here. So let's calculate that difference, right? The I minus whatever's in the stack. Let's pop from the stack because that'll never be used again, and let's just keep trying this until we can't, and then we're done when we traverse the whole thing. You could have like an early return here. You could say like if stack is empty, just return. So you could say like if empty, if you wanted to. That's fine too. In fact, you can even put it here. And I guess it doesn't matter too much, but yeah. Okay, so this will also work. Yeah. And so as far as efficiency, I think stack's just a little bit slower or something. You can probably use something else. You can probably use like an array or whatever, but this is basically linear time, so it's just not too important. Yeah, so this is going to be linear time because we're using a stack, we're populating, and then we're going backwards. So we're basically doing like a 2 pass. And in space, we have the stack, so a lot linear. And yeah, kind of good one. Honestly, there's some hard problems that use a monotonic stack, but the monotonic stack is not the whole solution. Like basically this one, the monotonic stack is the whole solution, and some problems like monotonic stack is half of it. And I do think those problems are some of the hardest because there's very few stack problems. They're like very rare, and in a lot of cases, it's very hard to figure out that you can use it. So definitely, if you can, give it a try. Also, another thing you can do with a stack is sometimes you won't necessarily be popping like the same direction. So you might have like a monotonic queue or something where you might be like pushing to the right, popping from the left. Like there's a bunch of different things you can do with it. So think about that as well. Don't just use a stack. You can use a queue. You can use a deck. Think about those kinds of solutions as well. They do happen sometimes. But yeah, it's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And like I said, I probably won't be doing every problem, but every second or third or whatever. I'm going to not do the easies, and if there's like some difficult problems or something, I'll do those. And then if I have some more free time, I'll probably start doing every problem again. We'll see how it goes. So thanks for watching, and I'll see you in the next one.